Welcome to the Deep Dive. Today, we're diving into a really persistent challenge in AI. It's all about how we build models that can genuinely understand and crucially remember information across incredibly long stretches of data. Think huge documents, massive code bases, maybe even hours of conversation. Our main source today is a pretty dense but fascinating research paper. It's called Atlas, Learning to Optimally Memorize the Context at Test Time. The authors are led by Ali Barouz. And our mission really is to unpack this. We want to figure out what exactly Atlas is, how it tries to overcome some major roadblocks for current AI models, and what it could mean for the future of AI. Especially, for handling truly enormous amounts of context.
Yeah, and this long context problem, it's not just academic, it's a real practical bottleneck right now. I mean, models like transformers have been amazing, right? Revolutionary. But the way they work, their attention mechanism, it just hits a performance ceiling.
Okay, let's dig into that. What's the issue with transformers?
Right. So standard transformer attention, it works by comparing every single piece of information, every token, with every other token in the whole sequence. That's super powerful for finding connections, even far apart, no doubt. But the computation, the memory needed, it blows up quadratically. Meaning if you double the length of the input, you need 4 times the memory in compute. Double it again 16 times, it just becomes totally impractical for really, really long sequences.
So they just can't, read a whole book and understand it in one go?
Pretty much, yeah. Not practically. And because of that, people have obviously looked at other things like modern recurrent neural networks, RNNs. These process data step by step sequentially. They can be much more efficient, scaling linearly. Often they have this fixed size internal memory state that gets updated as they go. And they've had success. But the paper argues, and others have found, that when you really push them on very long context understanding, or pulling out specific facts from way back, that's called in-context retrieval, or even just performing well on sequences longer than they saw in training, extrapolation, these RNNs tend to falter. They still struggle.
Okay, so the heavy hitters, transformers, and modern RNNs both have their weaknesses when things get long. What specific reasons does the paper give for why these RNNs aren't quite cutting it for long contexts?
The authors zoom in on 3 key design limitations they see. First one is pretty straightforward: limited memory capacity. Even with clever designs, that internal memory is fundamentally fixed in size. And the way information gets encoded into it, that puts a hard cap on how many distinct facts or patterns they can really hold on to from a very long input.
Right, limited space. What else?
Second, it's their update style. They tend to be very online, very moment to moment. This means the memory gets updated mainly based on the single newest piece of information coming in, while also trying to carry forward the past state. It's heavily biased towards the now.
Right, focusing on the immediate input.
Exactly. And third, the paper argues they often use simpler methods for managing that memory. They rely on standard optimization like gradient descent, which basically looks at first-order information, just the immediate feedback on whether a small change helped. This might mean they don't find the absolute best way to organize the information in memory. They can get stuck in what you might call local optima memory states that are okay but not great, especially for complex, long sequences.
So for you listening, picture this. You're trying to absorb a huge, complex manual. But imagine your brain can only really zero in on the last sentence you just read. And you've only got a tiny little mental notepad of fixed size. Plus, your brain isn't being very smart about what notes it keeps versus throws away from that pad. That's sort of the challenge AI faces with these massive inputs.
That's a really good analogy. And this leads into how the paper reframes the problem. They suggest looking at these models through a memory perspective. Think of them as sophisticated associative memory systems. And the core concept they introduce is test time memorization. Now, this is different from training. It's all about how the model's internal memory state changes while it's actively processing some input, a document, maybe a long chat history. The goal isn't to change the model's fundamental learned knowledge, the parameters fixed during training. It's about optimally configuring its internal memory to capture the key stuff within that specific context it's looking at right now.
So it's learning during use, but only for that specific interaction. The learning doesn't stick around for the next document it sees.
Exactly. It's about optimizing memory for the current context. Now, here's the key insight they build on. Existing models often update memory based on the surprise of the current token. How unexpected is this single word? But think about it, a really important event or idea in a long story might unfold over several sentences. It might not be surprising word by word. So the paper's big idea is shifting focus. learn to memorize the context itself, measure the collective surprise or importance of a whole window of information, not just react token by token.
Okay. So moving from reacting to individual words to grasping the significance of, say, phrases or sentences together.
Got it.
So let's get into Atlas itself. How does it specifically tackle those three limitations you mentioned: capacity, the online updates, and the simpler management?
Right. Atlas proposes specific solutions for each. Let's take them one by one. First, higher capacity memory. The paper mathematically shows that typical fixed parameter memory has inherent capacity limits. Making the memory deep using multiple layers helps, but maybe not fundamentally enough. Atlas's move here is clever. It uses what they call higher order feature mappings. Think polynomial kernels. Instead of the memory just seeing the raw input features, it sees more complex combined versions like interactions between features, polynomial combinations. This massively boosts the effective richness or dimensionality of the information the memory gets to work with. It allows storing much more complex patterns and distinct pieces of info without just bloating the number of input parameters. They show capacity grows significantly with the complexity, the degree of these polynomial features. And the intuition. Well, these polynomial features can approximate powerful functions used in things like transformer attention. Or you can think of them as a smart gating mechanism, deciding which combinations of input features are actually important enough to pass through to the memory.
And why does that matter to us, to you listening? It's like giving the AI a much more sophisticated set of mental hooks to grab onto different aspects of that long document. It can hold more varied details simultaneously in its working memory.
Exactly. Second, memorizing the context. We talked about how RNNs often get stuck updating based only on the very last token. The authors call this greedy memorization. It misses the bigger picture. Atlas brings in this new update mechanism, the omega rule. The key thing here is it uses a sliding window update. Instead of just looking at the last token T, it looks back over a defined window of recent tokens, say from TC to T. It optimizes the memory based on all the information in that window.
Okay. So it considers a chunk of recent history.
Precisely. And within that window, it uses these special decay terms, which act like hard gates. They let the model learn, depending on the input, which parts of that recent context window are actually relevant and should influence the memory update. It helps prune out noise from the immediate past. They built an architecture, OmegaNet, that specifically combines this omega rule with those higher order polynomial features we just discussed. The core idea is it learns to gauge the importance or surprise of the entire local context window, not just one token.
That feels like a really fundamental shift. It's not just remembering word. It's learning to grasp the significance of a whole phrase or sentence, or even a paragraph, as a unit within that sliding window you define. Like remembering the plot points of the last few pages, not just the very last word you read.
You've got it. Third, smarter memory management. So many models use fairly basic optimization like standard gradient descent for their internal memory updates. Just looking at that first order slope information. The paper argues this can lead to getting stuck in okay but not great memory states, those local optimized, especially when the context gets really long and the memory landscape is complex.
Right, you need a better map.
Exactly. Atlas tackles this by using a more advanced optimizer called muon. Muon is designed to approximate second-order information. Think of it like this. First order is knowing the slope of the hill you're on. Second order is also knowing the curvature. Is it a gentle slope or a steep ravine? This gives a much richer picture of the optimization landscape. This allows the model to navigate that landscape more effectively, find genuinely better memory configurations, and avoid getting stuck in those shallow local minima.
So it's using a smarter algorithm to figure out the best way to store things.
That's the idea. The Atlas update rule incorporates muon, using this more sophisticated approach to fine-tune its internal memory mappings dynamically. It's aiming for a truly optimal state for the given context.
So it's really a three-pronged attack. More memory capacity through clever features, looking at context chunks with the omega rule, and using a smarter optimizer, muon, to manage it all. That does sound powerful.
It is. And importantly, the paper shows these aren't just standalone ideas for Atlas. They can be used to generalize or enhance existing architectures too. They introduce things like deep linear attention, DLA, which basically takes linear attention models and swaps in a deep neural network memory using those polynomial features, showing the benefit of deep memory. Then there's DeepTransformers, which they frame as a strict generalization of the original transformer, but using this deep memory concept in potentially more powerful kernels. And DOT, which stands for Deep Omega Transformers. That combines the deep transformer idea with the Omega rule applying that context window update to a transformer-like structure.
Okay, so these variations aren't just random names. They're helping the researchers isolate the effects of each component, the deep memory, the polynomial features, the Omega rule, and show how they can build upon or extend even established frameworks like the transformer.
Precisely, and they stress that this isn't just theory. Practicality is key. The Omega rule and Atlas are explicitly designed for efficient, parallelizable training.
Which is crucial, right? Otherwise, it's just a nice idea on paper.
Absolutely. They use techniques like partitioning the sequence into chunks, computing updates within chunks in parallel, and then carefully managing the dependencies across chunk boundaries. For the Omega rule, they have masking strategies to avoid massive computation. For Alice, the way muon interacts with the memory allows for parallel updates. It's all engineered to be trainable on modern hardware at scale.
That's vital. So these are improvements designed to be actually usable. Okay, the big question then. Did it work? What did the experiments show?
Yeah, the results are pretty compelling across the board. On standard benchmarks like language modeling and common sense reasoning, Atlas and OmegaNet generally performed at the top among similar non-hybrid models, and even compared well against enhanced transformers. The authors attribute this success to that focus on memorizing context rather than just tokens.
Okay, good start. But what about the really long stuff?
That's where it gets really interesting. On long context tasks, they tested things like needle in a haystack, finding a specific sentence hidden in a massive document, and Babylon, which tests reasoning over extremely long narratives. On needle in a haystack, Atlas performed very well compared to other recurrent models. And on Babylon, this is the headline result, really, Atlas maintained high accuracy, over 80%, even at a context length of 10 million tokens.
Oh, 10 million. That's hard to even conceptualize. That's like understanding, I don't know, the entire Lord of the Rings trilogy plus The Hobbit, all loaded in at once and being able to answer questions about it.
It's a massive scale, yeah. And other strong recurrent models really started to degrade significantly way before that point. The paper directly credits Atlas's success here to that combination. The powerful muon optimizer managing the memory, the high capacity from polynomial features, and that context-aware Omega rule.
That's a huge leap for handling long-form information.
Definitely. And other experiments reinforce this. On benchmarks specifically designed to test memorization, Atlas came out on top overall, suggesting its components are doing what they're supposed to do, improve information storage. On in-context recall, pulling out specific facts, transformers are still very strong, but Atlas and OmegaNet were competitive and clearly outperformed previous state-of-the-art recurrent models. They helped close that gap. And on associative recall, which is about linking related pieces of information, Atlas showed the best performance relative to its memory size, indicating efficiency.
So it's not just good, it's efficient too.
Seems that way. And they also did careful ablation studies. This is where they systematically remove or change individual components of Atlas to see what impact each one has. And the results were clear. Every key part mattered. The deep memory, the polynomial mapping, using the Omega rule with a context window bigger than one, the muon optimizer taking any of them away hurt performance. They also showed performance generally got better as they increased the size of that Omega rule context window, confirming the benefit of looking at broader context.
So it really is a synergy of all these different innovations working together, not just one magic trick, but several smart ideas combined.
Exactly. And just quickly on the architecture itself under the hood, it uses fairly standard building blocks like linear layers and short convolutions. The real magic is in that memory module, often a couple of MLP layers, maybe with gating, but crucially, how it's managed by the polynomial features, the Omega rule, and muon.
Okay, so let's try and wrap this up. Recapping this deep dive into Atlas, it seems the paper introduces some really significant ideas. High-capacity deep memory using those polynomial features. A new Omega rule that lets the model memorize context over a window, not just single tokens. And smarter memory management using the muon optimizer. And all of this is focused squarely on letting AI handle and remember information over incredibly long sequences way better than before.
Right. And the results, especially that mind-boggling 10 million token performance, suggest this is a really promising direction. It could lead to AI that doesn't just get lost or forget the beginning when dealing with huge amounts of information. Think about future models that could genuinely understand and use information from, entire textbooks, vast legal archives, or really long, complex conversations, all within a single interaction.
It really underscores that the future of AI isn't just about scaling up existing models. It's also about fundamentally rethinking how they process information over time, especially how they remember and understand context in these long sequences. Atlas seems like a big step in that direction.
And that leaves us with a really interesting thought, building on this test time memorization idea. If AI systems get really good at optimally memorizing the specific context you give them during your interaction, tailoring their internal state just for that data, how does that change how we interact with them? Do we start expecting them to have perfect recall of everything we've ever discussed or shown them within that session? And maybe more importantly, how do we ensure transparency? How do we know what they're actually remembering and basing their answers on, especially when the context pool becomes potentially vast and dynamically updated? Something to think about.
Definitely food for thought. Thanks for joining us for this deep dive.